When an ideal gas is compressed, according to Boyle's law, the graph of PV against P is a straight line parallel to the x-axis. You can see this on the screen later. Hydrogen does not behave as an ideal gas. Hence, when a fixed amount of hydrogen is trapped in a cylinder and the pressure is increased, the graph of PV against P is not that expected of an ideal gas. Click play button to see the graph of hydrogen as the pressure increases. The graph shows a positive deviation from ideal gas behavior. Look at the graph. Does hydrogen behave more like an ideal gas at low pressures or high pressures? Answer: low pressures. The result of this experiment might suggest that there is something in a real gas, such as hydrogen, that is making it behave differently from what we expect of an ideal gas. This time you are going to look at the graph of PV over nRT against P for nitrogen. Nitrogen is another gas that does not behave as an ideal gas. Click play button to see the graph of nitrogen as the pressure increases. How is this graph similar to the hydrogen graph? Answer: it starts at the same point and rises steeply at high pressures. The graph has a negative gradient, that is, a negative deviation, at first, before it starts to rise and produce a large positive deviation at high pressures. This is more complicated than the case of hydrogen. It suggests that perhaps there are two factors operating, one at lower pressure and one producing the opposite effect at higher pressure. Now you are going to look at the graph of PV over nRT against P for carbon dioxide. This is another gas that does not behave as an ideal gas. Click play button to see the graph of carbon dioxide as the pressure increases. Like nitrogen, the graph has a negative gradient, that is, a negative deviation, at first, but goes down much further than nitrogen. Again, it starts to rise and finishes up showing a positive deviation at high pressures. Again, this suggests that there are two opposite factors in play, one producing a positive deviation and one a negative deviation. For which of the three gases, hydrogen, nitrogen and carbon dioxide, is there the biggest negative deviation? Answer: carbon dioxide. The gas laws such as Boyle's law and Charles' law are true for ideal gases. For an ideal gas, we make some assumptions. The molecules in the gas are moving at rapid random motion. The volume of the molecules is negligible compared with the volume occupied by the gas. There are no forces of attraction or repulsion between the molecules. Look at the two pictures on the screen. In which picture, left or right, is it false to state that the volume of the molecules is negligible compared to the volume of the container? Answer: right. In which picture, left or right, is it false to state that the attractive forces between the molecules are negligible? Answer: right. Which gas, left or right, is more like an ideal gas? Answer: left. Here you can look again at the graphs of PV over nRT against P for hydrogen, red, nitrogen, blue, and carbon dioxide, black. The positive deviation that occurs in all three cases is caused by the volume of the molecules. This becomes more significant at high pressures when the molecules are closely packed together. The negative deviation occurs when there are strong forces of attraction between the molecules. In which gas are the forces of attraction strongest, and in which gas are they the weakest? Answer: strongest, carbon dioxide; weakest, hydrogen. A real gas behaves more like an ideal gas at low pressures and high temperatures. Suggest why a real gas behaves more like an ideal gas at high temperatures. Answer: at high temperatures, the particles are moving faster, and so forces of attraction are less significant. Summary: the equation PV equals nRT is true for ideal gases. In an ideal gas, the molecules are in a state of rapid random motion. In an ideal gas, the volume of the molecules is insignificant compared to the total volume of the container. In an ideal gas, there are no forces of attraction or repulsion between the molecules. Gases behave more like ideal gases at low pressures and high temperatures.